Welcome, everyone. I think I did the right thing. It's about 12:10. So I hope many of you at least have had a chance to eat a little bit, enjoy the rest of your lunch. I'm here to introduce Alejandro Toriello, and it's a pleasure to do that. For those of you who don't know Alejandro yet, I'll tell you a few things about him. So he has a long history with Georgia Tech in the sense that he not only did his undergraduate here, but also his Ph.D. He graduated, or he finished his Ph.D. in 2010, I believe. Then he accepted an assistant professor position at the University of Southern California, also a very reputable institution, but we had been so impressed with his early work here at Georgia Tech that we tried our best to convince him after a few years to come back, and we succeeded, which we were very happy with. So he came back to Georgia Tech in 2013. He has been promoted to associate professor not that long ago, but well deserved. And he's one of a few people in our group that is very interested in all problems related to last mile or same-day delivery. And he's going to tell us a little bit about his thought, visions, and work on that particular topic. And it should be incredibly insightful and entertaining, I expect.
We hope.
So, Alejandro.
Thank you. If you're counting, that's 14 years I've been at Georgia Tech in one capacity or another. So I like to say that I'm like a bad cold, that they just can't get rid of me. So thanks very much for being here. I'm happy to be here as well. I'm excited to talk to you all. I'm going to try to make this as informal as possible, so please interrupt me whenever you feel like. And if we don't get to the end, it doesn't matter. So just please feel free to interact, raise your hand, interrupt me, anything you like. I'll point out that this is joint work with a couple of people. So my colleague Alan Herrera, who hopefully many of you all know, and a couple of students, one former student, Matthias, who is now a professor at the Catholic University in Chile, and a current student, Alex, who is in the audience and who can correct me if I say something wrong. So what are we going to talk about? So I like keeping this slide up as an introduction because when I started giving talks about same-day delivery, this really did seem like the pie in the sky. And I'm going to keep this slide in my introduction to these talks until I have to remove the question mark, because this is at some point going to be actually what happens. For the time being, it's still a little bit more of the pie in the sky. But there's still, even if you don't yet believe in drone delivery, there's many reasons why you want to study problems like the one we're going to talk about today. So there's at this point already a very well established, several years worth of these different service offerings from a variety of different companies. The obvious highlight being Amazon, but many others. And so it seems like an interesting, very exciting area to study within logistics. There's lots of stuff going on. And so what I'm going to talk about is basically what we've been looking at over the past few years of problems to relate in this area. And so try to maybe set the table a little bit at the beginning and talk about some context, and then we're going to spend probably the bulk of our time talking about operational issues, which is where we've done more research up to this point. And this is essentially what I'm going to show you is what became most of Matthias Clapp's thesis. And then I'm going to talk a little bit more briefly at the end, or towards the end, about tactical design issues, which is an ongoing research project that we're doing right now with Alex, which we're very excited about. And then we'll wrap it up from there. So just let's set the stage. Why do we care about these problems? So at this point, I think e-retail or e-commerce is really retail. This is a growing and completely established part of the economy and of how consumers buy products. So I put up a few salient facts up there for you all in case you hadn't seen them before. So it's been for the last 5 years, e-commerce or e-retail has been at least 10% of total retail spending. And at this point, it's more. And at this point, we're projected this year to reach $2,000 per online buyer spent per year. And so, at least thinking of myself, I think I'm probably above the average already. And it's amazing how quickly you transition into being one of these buyers, and how once you go that way, it's hard to go back because it's so much more convenient, so much easier. The big player in the room is, of course, Amazon. So Amazon this year is essentially breaking the 50% threshold. They're going to be more than 50% of e-commerce in the US. Now, I should point out here that when this statistic includes the Amazon marketplace, which is, of course, processed by Amazon, but not products that are sold by Amazon. But of course, they take their cut of that as well. And this is a big part of their revenue stream. And so, of course, if you count all of that together, Amazon is more than 50% of all of the stuff that's sold online in the US. And there's a bunch of downstream impacts of these facts. So worldwide, Amazon is now the second largest US retailer. So just to be precise there, of all private US companies, if you count their global employment force, their global workforce, Amazon is number 2, Walmart is number 1. Now, of course, you can see this has a bunch of impacts in terms of how the economy works, and it has a bunch of impacts in things that are salient in the news nowadays, things like the development of automation, and are people going to be replaced by robots and this kind of thing? Because you can see the difference in the workforce when you go from a retail operation to something like e-commerce operation. Even though these are big companies, there's a change of magnitude, order of magnitude in the number of people that they employ. And of course, there's big news related to this. For example, the fact that Amazon has just decided to establish a $15 per hour, I guess I wouldn't call it minimum wage, but the minimum salary that they pay their employees. So any kind of decision like this that Amazon makes has a tremendous impact on the US economy and the world economy. And so, of course, this all means that the kinds of problems that Amazon cares about and the kinds of problems that are important in e-commerce are just important problems, period, in the economy. And so this is just a chart of the projections that I was talking about before. So as you can see here, this is this year, and we're already almost at 50%, and we'll exceed 50% of Amazon's share of e-commerce next year. And the really remarkable thing is just the rise in the total number that we're talking about here. So if you think about what this means in terms of total e-commerce in the US, this year it's about half a trillion, and it'll be, it's going to go up by another, 150 billion next year. So it's the growth is explosive. And so as this sector grows, it becomes more and more important to compete. It becomes more and more important to drive innovation in the sector. And so the ultimate holy grail is to compete with brick and mortar stores, right? To offer the same level of service that a customer expects in a brick and mortar store, right? And same day delivery is this idea, right? The idea that I don't have to wait any more than I would have to wait for a product if I want to get it online versus getting it at the store. And in some senses, it's even more convenient because I don't even have to leave my house, right? So this is one of the things one of the innovations that's really driving the sector right now. However, on the operational side, or on the side of the administrators, this really causes a lot of problems. So the last mile of this distribution, when you go into something like same-day delivery, is extremely costly because the number of orders you're delivering is much, much, much lower, right? So that you can't take advantage of the economies of scale that you would in a more typical distribution system, like even a next-day distribution system, where you can sort of pull everything together, right? I looked up, there's a recent survey, this was done last year, a survey that McKinsey did, that shows that less than a quarter of customers, of e-commerce customers, are actually willing to pay for delivery services. The vast majority of the customers essentially want you to do it for free, or they're willing to take the fastest delivery option that is available for free. And even the ones who are willing to pay are not willing to pay more than a very small amount, say a couple of dollars, for this fast delivery. Okay? However, I have some question personally about what this exactly means, because if you think about something like Amazon Prime, what Amazon is really doing there is making you amortize these costs of delivery, and it's a question of behavioral economics, really. You know, if you pay a single flat fee once a year, right, and then you get your deliveries for free, you feel like you're getting them for free, but that's a psychology more than anything else, right? But this clearly has an effect, and Amazon is taking advantage of this. So in some sense, this survey is asking people what they think, but then if you look at what they're really doing, you know, they seem to be willing to pay for the service. It just depends on how you charge for it. Okay. Okay. So then, when you actually think from a manager's perspective on what's new about same-day delivery, specifically from the distribution or transportation side of things, what's going on here? So the typical model, the traditional delivery model, will have all of the order management, the picking, the packing of the orders, everything happens before you do any last mile distribution, right? So if you think even of next day delivery, what's going to happen is you're really going to rely on a very agile, very nimble backbone network. Think of something like the air networks that UPS and FedEx have to get stuff from one side of the country to the other overnight. And this relies on a really sophisticated, a big investment of your backbone network. But when you're actually thinking of this from the last mile perspective, this is essentially the typical think of UPS, the problem that the driver faces in the morning, right? So you have a local warehouse, and a bunch of packages have come in overnight, and the problem is I have a bunch of packages, I know exactly where these packages need to go, I have to divide them into subsets that go into each truck, and then plan the route for each truck. And this is your classical vehicle routing problem that we have studied for, at this point, several decades. And this is a problem that from a research perspective, and I think from a practitioner's perspective, is sort of very well understood in terms of last mile distribution. So the challenge for same-day delivery is that you now have to do these two things simultaneously. The acceptance of orders, the picking of orders, the packing of orders happens at the same time that you're already dispatching orders that were ready before. So everything is happening concurrently throughout the day. And so for the purposes of this talk, we're going to focus specifically on a common deadline. So think here of I'm not ordering a pizza. I'm not ordering Grubhub. I'm at work, and I remember that I need to order something like, I don't know, I need my toothpaste, or I need my dog's food or something like this, and I'm happy to just have it be waiting for me when I get home tonight. So I'm not ordering my lunch. Now, if you are curious about those kinds of problems, like Grubhub and Uber Eats and Amazon restaurants, these kinds of things, I haven't personally worked on this lately, but some of my colleagues have, including Martin and Alan, and they have specifically worked with Grubhub. So if you have questions about those kinds of problems, then ask them. So in that sense, that is obviously an even more challenging problem in terms of economies of scale. And it's more applicable for perishables, for food, for flowers, for groceries, these kinds of things. But we're going to focus more on the common deadline type problem. Okay? Any questions? Okay. Terrific. So I stole this picture from one of Alan's talks because I think it's very illustrative. This is essentially the problem I was describing before in pictures. So if I had all of my orders ready at the beginning of the day, then maybe I could do something nice like this. But the color coding in this picture tells you some of the orders are early, some of the orders come a little bit later in the day, and some come very late in the day. And because the orders come in this way, I I can't wait until the end of the day to serve everything and do this, because then the orders would be delivered too late. So I basically have to deliver while orders come in and do something that's way less efficient. This is essentially the problem with what we're talking about. So with this kind of setup in mind, let's think of a basic operational model, and let's see if we can extract some insights from it and some thoughts about how a dispatcher ought to manage a system like this. And so our basic operational model is going to have a couple of components. So we're going to look at it at the level of a single dispatching facility. So think here of a local warehouse, a local DC, or perhaps even a retail store if you're doing omni-channel fulfillment. And you've already decided at some higher level what store or DC is fulfilling orders for a particular address. So you've already partitioned your urban area, let's say, into service regions and identified the DC that's going to serve that region. And you have your known service area, and to keep it simple, we're going to assume that there's a single vehicle that's making the deliveries here. And so you have some kind of a same-day delivery horizon. So this is the time of day in which you're accepting orders. And the orders are going to come in, but it's random. I don't know where they're going to pop in from. I don't know what time of the day they're going to pop in from. So I, in some sense, have taken my service region and I've split it up into neighborhoods or city blocks or something like this. And there's some underlying random process that's producing orders. And this is probably based on a probabilistic forecast that I have that's based on data that I already have. And I'm going to assume that all of the orders that pop in over this horizon are served, either by my delivery vehicle or at a higher cost by a third-party operation at which I offload all of the orders that I could not serve at the end of the day. And if you don't like that assumption, then think of that as the lost sale cost for the orders that I could not serve. Okay? Both of those are equivalent for our purposes. And so when the vehicle is available, the dispatcher has to decide what to do with the knowledge that the current dispatch is going to influence the total cost of the operation, but also how long the vehicle is occupied and the next time at which the vehicle will be available to make another dispatch. So of course, my decision has it has an impact on my cost, but more importantly for our purposes, it has an impact on when I can make my next decision. So that's really the key here. And so for the purposes of our discussion, let's assume that we're minimizing our total operating costs, which will be our routing costs. But you can equivalently also think of maximizing your order fill rate if you prefer that. In which case, what I would want to do is minimize the number of orders that are served by the third party. So we can also think of that, and I'll come back to that at the end. Okay? And so to make things even simpler, what we're going to do first is focus on the absolute simplest version of the problem that I can imagine that still captures the elements of it that are new and interesting to us. And so what we're going to do first is think of the most restricted geometry that we can think of, which is a single line. So this is the DC. These are the potential order locations, and they're all going to be on the same line. So why are we doing this? So clearly we're not at this point talking about a practical problem anymore, but the single line geometry is the situation in which you maximize economies of scale, because the time and the cost of the dispatch is purely given by the farthest order you choose to serve in any dispatch. So this maximizes economies of scale. So if the system is not economical with this geometry, then you're going to have real problems in general. So what we're going to try to do is analyze this system for a little bit and extract insights from it that we can then apply to a real road network. That's the idea here. Okay? So this is a picture of a schematic of what the process would look like. So in this schematic, the horizontal axis is time, and the vertical axis is how far away orders show up from the depot. And at any point in time, I have to decide how far away I'm going to dispatch the vehicle, in this case maybe 2 units away. And when I dispatch the vehicle 2 units away, it comes back at some later point. I've covered all of these orders. These orders I did not cover, so they remain open. And some new orders might appear randomly, and then the process repeats, right? And I keep doing this until the end of the day. And so what we're going to try to do first is try to understand this very, very simple system and see if we can extract some structural insights that help us understand how the real system would operate. So here's a representation of an even simpler problem. In this problem, I have removed the uncertainty. So now I not only know, I not only have a simplified geometry, I have a simplified order system in which I know exactly when the orders are available. I still can't serve them before they become available. So think of this as the point in time at which this is the point in time at which this order, which has to go to this distance, has been picked and is ready for me to dispatch from the depot, from the warehouse. And this is a schematic of what one possible day might look like if I do this. Okay. And this is also an example of a bunch of dispatches that I might make in order to serve these orders. So if my objective is to minimize the total time that my vehicle is traveling, can anybody suggest some possible improvements to this example or any corrections to my dispatch plan?
You could remove the first dispatch.
And why could I do that, Marlon?
Because it will cover it with the second.
Yes. So one simple observation is, again, because this is a simplified geometry in which everything's on a line, this dispatch goes farther and leaves later than this dispatch. So of course, everything that I covered with the first dispatch, I could just as easily cover with the second dispatch. So that tells me that I will never send an early dispatch closer if a later dispatch will go farther. Okay? And this is kind of a nice thing to keep in mind. So hold that thought. Is there anything else about this solution that I might make better? So remember, what I want to do is cover as many of the red dots with a gray rectangle as possible, and I want to keep the heights of the rectangles as short as possible. I see a bunch of students who have taken classes with me in the past or are taking classes with me now. Any suggestions?
Just a question. So
Yeah.
a
Yeah.
dot which is not in the gray area has not been served?
We will outsource that dot, yes. So, for example, suppose you can see here that the vehicle departs, comes back at this time, and then waits before leaving the next time. What if I delay my departure so that the timing works out and the return of the vehicle coincides with the next departure? And if I do that, then this order here, which I am not covering right now, I can cover at no additional cost because I'm going just as far. Okay, is that clear? So if I make those kinds of fixes, I might get a solution like this, right? In this solution, I see a couple of things. I see early dispatches go far, later dispatches stay closer, and the waiting is banked at the beginning of the day. The waiting is up front. Once the vehicle starts operating, the vehicle is in continuous operation until the end of the day. And so those are structural insights from a very, very simple example that are going to prove particularly useful. Yeah?
I just had can you go back to those reasons?
Yes.
So I'm just curious, so the vertical blue line is,
How far I went.
because you're traveling over distance, your time to get there.
Yes, so exactly right. So if you were to plot this in terms of where am I at any point in time, the triangle would actually be an isosceles triangle, but I can only serve orders that were ready at the time of my departure, which is why it makes more sense to plot a vertical line. Because imagine essentially if you look at this order right here. So if you think about it, right, I would get to that distance at this point, but I cannot serve this order because it was not picked by the time I left. Does that make sense? It's a great question. Yes, Marlene.
Maybe you'll talk about it later, but this figure suggests that you hire your driver in the middle of the day instead of in the beginning of the day. Is this a general?
Well, this figure suggests that your resources, both workforce and vehicle, are not used for same-day delivery at the beginning of the day.
So they could be used for something else. Yes, and we'll definitely talk more about that. Okay, so the takeaways are precisely the two things that I pointed out. The dispatches decrease in length. So think of this qualitatively as, at the beginning of the day, I'm more willing to serve a larger number of orders and to go farther away from the depot. Later in the day, I'm going to restrict myself to sticking closer to the depot and kind of making shorter runs. And the waiting is all up front. Once I start serving orders, I'm essentially going to want to keep the vehicle in operation. And for this specific problem, we can use these structural insights to then solve the problem quite efficiently. But I still haven't told you what this means for the actual problem. And even here, I'm not even talking about the actual problem, but the actual one-dimensional problem, which is in which I don't actually know when the orders are ready, right? So the real problem looks a little bit more like this. So maybe I have a couple of orders that came in overnight and are actually next day delivery orders. And then I have some forecast of when different neighborhoods might place orders throughout the day. And I have to make a plan now, even though I don't know what's going to happen later. So the insight that's going to help us take what we did before and translate it into this context is to basically say, well, let's take a forecast like this that tells us when we might see orders, and let's break it up. And let's turn those into copies of a particular order. And these copies are going to be essentially weighted by the probability that an order actually shows up at this time. And now I have a version of the problem I had before, where I have these multiple copies of orders showing up in different places, which sort of represent my forecast. But now I'm going to treat each copy like an individual order, and I'm going to solve the problem like I solved it before. And so what this dispatch right here means is if this order shows up at this time or earlier, I cover it. If it shows up later, it's too late and I let it go. Either I outsource it or it's a lost sale, depending on my context. And so this gives me a dispatch plan that I can make at the beginning of the day that basically roughly tells me at this point of the day I should expect a dispatch and it should expect to go this far, and it'll come back, and then there's a next dispatch at this point in the day which I expect to go this far. That's roughly the idea, right? Now, of course, once you make the plan, so this some folks might call this a route-based plan, perhaps, or a route-based policy. And so, of course, once you go back to what's really happening, you will then observe things. The forecast is not always going to be accurate. Things will happen later or earlier than when you expect them. And then something like this might happen, and then you'll say, well, there's no point in me going this far when there's nothing there for me to do, so I'll just delay and go a little shorter, for example. This is kind of the idea. Now, this is a static dispatch plan. So not very dynamic, not very adaptive to what's happening in reality. So even with these short fixes, you get a plan, but you don't get a very nimble plan. You don't get a very good plan. What you really actually are going to do in practice is essentially do this every time. So every time the vehicle is ready to go, you will compute one of these plans, but only implement the first part. And then when you come back, you update with the new information you have. The things that are not known, you keep in the forecast mode, and you make it the next decision, but only implement the first dispatch again. So you always make a dispatch with as much information as you have at the moment. And if you do this, this actually works really well. And so this is what sometimes is called rolling out. Essentially, at every point in time that you have to make a decision, you incorporate everything you know right now. So the orders that have already arrived, plus the forecasts for the orders that might arrive in the future, and you make that plan, but you only implement the first part of that plan. Okay? Does that make sense? And I'll show you an example of what this means in an actual problem in a second. Okay? Questions up to this point? Yes?
So you forecast both as to when and how far when those orders will arrive and how far they will be?
Yes. So think of this as
both elements as important? Or?
Yes, because as I was pointing, sort of, if you think, even in this simplified context, if I expect a faraway order to show up early in the day, I'm much more likely to want to go to service it than a faraway order that shows up later in the day. So what I'm going to really have in practice is I'm going to have
think of this as for every neighborhood or every city block in my service area, I'm going to have some kind of a probabilistic forecast that says these many orders per hour are showing up, or something like this on average, or the probability of certain things showing up. And that's what you would do. Other questions? Yes?
Yes. On your graph, the distance, the y-axis on the distance, I understand distance means something, it means time. Why wouldn't that be the time to make the delivery and return rather than the distance?
It's both. So we're assuming here that they're proportional.
Okay.
So the time, I've scaled my time and my distance such that the time it takes for me to make a dispatch that goes this far returns me at this time.
Yeah,
so it's both.
Yeah, density with a lot of red dots there rather than the distance. It looks like you would build a time-based rather than distance-based. Because if you have something far out, it's going to take you long. But if you have a lot of them in a lower space, you would want to dispatch at a quicker time based on that time.
Yeah, so the one thing I'll say here is this, at this point I'm not incorporating service times. So you're right that if I have a service time, then I will have to take that into account, and that will impact this plan slightly, and you might want to do that then, yes. Other questions? Okay, so enough with simplified examples. Let's talk about something that's a little more realistic. So now think of really a general network topology. So I have a road network, and I've identified nodes in this network to be the neighborhoods or the city blocks or the addresses that are of interest to me within my service region. And now I'm gonna have to sort of do the same thing I just did, but actually route this vehicle through this network from the depot and back. And so this is an example of what one of these problems might look like, as well as a solution to the problem. So think here of the number as being how many hours were left in the service day, in the vehicle's operating day, when this order showed up. So a 6 means this order showed up very early in the day, and a 1 means this order showed up very late in the day. And so in this particular case, the example that I'm showing you is I have 2 dispatches. One leaves 3 hours before the deadline and takes 1 hour to serve these orders down here. And then a second dispatch leaves when there's 2 hours left, and essentially the vehicle is at that point in operation until the end of the working day. Okay? So I will point out right away that this solution breaks that rule that I had said before of the longer dispatches first and the shorter dispatches second. This is a case where that relationship is broken because, of course, in practice you would not expect that to always hold. Okay? Is the example clear? Okay. So then let's think conceptually of what this means if we follow a similar reasoning process that we just did for the simple one-dimensional case. What does that mean for the general network topology? So now think of the y-axis not as a distance anymore, but simply this is like a Gantt chart, right? This is a different point in the y-axis for every potential customer location, for every neighborhood. And in the deterministic context, so if I know exactly when an order is ready to go, I might have something like this. And then I might have a solution that looks like this. So this solution says, I dispatch the vehicle at this time to serve these 2 orders, visits this order first, this order second, and then comes back. And then I make a second dispatch that serves these 2 orders and visits this order 4 first, then order 3, and then back. So this is no longer going on a line. This is simply conceptually what would be the order in which I would visit these customers. Is that clear? Okay, great. So just like in the one-dimensional case, even though I can no longer guarantee that the distances are going to be decreasing, I can certainly, in a deterministic context, if I know exactly when every order is going to be ready, I can once again push all the waiting to the front and push all the operations to the back. So once again, I can expect that I would have a time at which I accumulate orders, but then once I decide to start my operation, the vehicle and the workforce will be constantly working for the rest of the day. So once again, here I have this is managerially, this kind of makes sense, right? You're basically going to have an off period and an on period. You're going to have a point in time at which you just let enough orders accumulate, and at some point you start dedicating the resource, and at that point the vehicle is essentially operating for the rest of the time that it has to be. So obviously there are differences. So what are the differences here? We cannot rely on this very simple geometry to do the analysis. We now have to throw this model to a much more of a workhorse, in this case an integer programming solver of some kind. For those of you who are familiar with integer programming models, and specifically for routing models, what we basically have to solve here is something that's called the price collecting traveling salesman problem that has a bunch of interesting side constraints. In this case, there's order release times, which means an order cannot be served before its release, which in this case would be when it's picked and ready to go. And the pickups occur at the depot. So this means I'm not designing a single vehicle route. I'm designing a multiplicity of routes in which each route serves orders that were ready at the moment in time when the vehicle left the depot. Mark.
Why is this a TSP and not an orienteering problem?
Potato.
Okay.
It just depends on what you want to call it. So I say price collecting TSP, but some people call it when it's profits, they call it orienteering. It's the same thing. Yeah. Other questions? What? Nobody else wants to talk about orienteering? Okay. Just kidding. Okay, so for a deterministic problem, you would basically solve an integer programming model of this kind. And so I'm not going to promise that it's going to solve in seconds, but it's going to solve in minutes. So with the integer programming technology we have nowadays, you can solve a model of this kind in minutes or even less. Okay? And so how does this work in the general case? The analysis is essentially very similar to what I was describing before. So I now replace my known order time with an order forecast that says I might get an order sometime in this span of time. I might get an order sometime here in this span of time. I might not. And I replace all of those, I replace the forecast with a bunch of copies of those orders, and those copies are once again sort of discounted by their probabilities. And now I have a problem pretty much like what I had before, and I can come up with a route plan. Kind of like what I did before, except now it's an actual route plan. And it might look something like this. And then just like in the other version of the problem, this route plan tells me, here's what I will do if the orders show up by the time that I plan to make the dispatch. And so, of course, this is kind of my coverage region, so to speak. For each of these orders, if the order shows up in the time that's identified by the gray rectangles, then I will cover it. And if it doesn't, then I won't. And so if I have a realization which occurs after the coverage moment, so for example, this one, then I can make an update. I can simply say, well, that order didn't show up in time, so I'm not going to cover it in this particular case. Does that make sense? And so this is the basic idea, although once again, if you simply implement this plan and make these simple updates, you've got a much too rigid plan that's not really going to be good in practice. So what you're going to want to do in this case is do the rolling out that we talked about before. Every time you need to make a dispatch, you will essentially incorporate all the information you've got right now. So that includes the actual orders that have arrived and are open, plus the forecast for the orders that might show up in the future. You solve a model of this kind, and you implement the decision it tells you to make right now. And once the vehicle returns and you have to make another decision, you update your information and repeat. Okay? And here's an example of what this looks like if you try to test it on an actual instance, on something more closely resembling like a road network and order forecasts that kind of look realistic, this kind of a thing. So I'm basically showing you what happens if you just implement the plan that I showed you before with no updates and no dynamic changes. And then a bunch of versions of this updating or this rolling out that I was describing. And what you can see is basically that, as you would expect, the cost goes down, and also the interesting thing that the thing that we were not expecting is also the variance goes down. So you lower the cost, the expected cost, and you are more confident that that's what the cost is going to be. In addition, so in this version of the model, we're assuming that you outsource all unserved orders to a third party at the end of the day, and you're essentially paying a cost that's equivalent to just a direct delivery for each of those orders. And what the fill rate here is describing is how many of the orders did we serve ourselves. And you can see that by being nimble and dynamic like this, you lower your cost, but you don't hurt your fill rate. You actually improve your fill rate, which is kind of nice because you are essentially saying you can serve both objectives simultaneously. So if you're adaptive, if you're nimble, if you take advantage of the information as it's revealed to you, you can actually improve your service as well. Is that clear? Okay, so back to fill rate. So I said at the beginning that in some sense you can choose whatever objective you like. So you can choose an objective that talks a little bit more about operating costs, which would want to minimize the routing cost as some proxy for the workforce costs and the vehicle utilization costs and these kinds of things. But if those costs, in many situations, those costs are going to be secondary to the lost sale cost, let's say, if you can't serve an order for some reason. And in many of these models, people care much more about actually serving the orders. That's really the only objective. And so in that case, you would want to do something like maximize the fill rate. And so our experiment here is basically showing you a thought experiment of what happens when you do this. So think here of alpha as how much do I penalize myself for not serving an order, and the relative weight that I give not serving an order versus the routing cost. So when I say alpha equals 1, this is the setup I showed you before, where I can essentially outsource to a third party and every order is just that I don't cover myself, I cover with a direct delivery. Alpha equals 2 means that direct delivery costs me twice what it would cost to send my vehicle to do it. This would be if the third party charges you a high premium. And then 100 basically means I'm losing that order if I don't serve it myself. So I must at all costs serve orders, if at all possible, and the routing costs are secondary and are only simply, I just include them as a tiebreaker, basically. And this sort of shows you what happens. So the punchline here is to increase your fill rate even a little bit, you have to increase your costs by a lot. So we find this to be kind of an interesting insight because a lot of people are concerned only with maximizing fill rate and don't care about the operating costs. And what our experiments show is that that last percentage point of fill rate that you're getting is costing you a significant amount if you care at all about operating costs. And let me show you one specific example of this. So this is the example I showed you at the beginning. The same exact data is sort of like, what if we had this data, but in one case we were optimizing routing costs, and in the other case we were optimizing fill rate. And this is the solution I showed you before, which looks reasonably economical, looks reasonably kind of like well organized. If you want to serve one more order, you have to do this thing over here. So you have, instead of 2 dispatches, you have 5. And the routing part of the solution goes up by about 50%. So the punchline here, if you want to take one thing away, is simply that you will see very, very high decreasing economies if you really are pushing fill rate to the limit. And you might want to think about, is it really, is there some middle ground at which you're willing to live with? Okay? Questions? All right, so in my remaining time, I'm going to sort of take a step back and think then about everything we've seen up to this point is, what would a dispatcher do? So I have my service region defined for me, I have my horizon defined for me, I know what the forecast is, and I'm simply just dealing with it as it comes. But so what if we're going to take a step back and maybe think a little bit more about designing the system and about how big should our fleet be for same-day delivery? How many resources should we dedicate to this service? Or how late in the day should we offer the service? So this is the kind of questions we're actually thinking about now. I'm going to give you just a simple example of the kinds of results that we've come up with. So if you take a step back, the question then is like, instead of worrying about the nitty-gritty, What if we just worried about what's going to happen on the average in any given day? So I still have the same setup. I have a single depot or fulfillment center, and this fulfillment center has some established service region in which it's going to serve same-day delivery orders. And I want to sort of think of what is this dispatcher going to see on average? So instead of thinking of a probabilistic forecast, let's just take orders as arriving at some constant rate, such that over the service horizon, the constant rate will give me the number of orders that I expect on an average day. So if on an average day I expect, 100 orders, and I have 10 hours in my service horizon, that means 10 orders an hour. And they're spread exactly evenly, so there's no unpredictability here. I'm just seeing kind of a constant arrival of orders. And when they show up, I don't know where they're going to show up. They're going to show up randomly somewhere in my service region. Okay? And then to serve them, and all of them have to be served. All of the, I'm going to essentially make it really simple on myself, and I'm going to say I have some point in time at which the orders accumulate. I stop accepting new orders at this point in time, and my vehicle or vehicles have to be back at some later time. So I'm making my problem, I'm trying to simplify a lot of the bells and whistles that I had before and simply looking at something very, very simple. And I'm going to further simplify the problem by not worrying about the routing too much in detail. So if I'm operating the system, I have to worry about when is the vehicle leaving, when is it getting to this address, when is it getting to this address. But taking a step back, if I say, well, on average, these many orders will show up, and I expect them to sort of be randomly dispersed within my service region, then I can do an estimate of how long it's going to take to serve those orders. And these kinds of estimates are used a lot in logistics context, and you can think of this as if maybe I would simulate 100 different order locations and then figure out what the routing cost is for those orders or the routing time. I can fit a model of this kind using regression, and I get very, very accurate measurements. But once I do this, I don't worry. This is not going to tell me at what time am I visiting this address. It's not going to tell me anything like this. It's simply going to give me an estimate for how long the vehicle is going to be out. Okay? So we're going to use this to simply look at what does the dispatcher expect to see over the course of the day. And so I'm showing one example down here of what the dispatch, what the operations might look like, right? And what I'm saying here is this is my horizon in which I accept orders. And let's just pretend maybe that I split my horizon into 3 equal parts. And so at every third, I dispatch the vehicle with whatever's accumulated so far. The vehicle comes back at some point. I wait till the second third. I dispatch the vehicle again, and then one last time at the end of the day. This is one example of what I might do on an average day. And I'm going to use this kind of this model to sort of do some what if analysis and say, what if I did this? What if I did that? What if I increased this? What if I decreased that? This is the idea. So first, think of the case in which I don't have a single vehicle. I have a bunch of vehicles available to me. What would I want to do? So it turns out what you want to do in this case is have the first vehicle wait and accumulate as many orders as possible until the point in time at which that vehicle leaves and has just enough time to come back by the deadline. And then rinse and repeat. The second vehicle starts accumulating the orders that showed up after the first vehicle left, and at some point that vehicle has just enough time to leave and come back right before the deadline. And that would be, in this case, the pink dispatch. And then, in this case, there's a third vehicle that accumulates the remaining orders until the end of the service window, and then leaves and comes back. But it might be, depending on where you set the end of your service window, that you only need 2 vehicles, or you might need 4. It depends. Okay? Now, I've made the simplification here that the service vehicle serves the entire service region. So I can't tell one vehicle to go only to the west and the other vehicle to go only to the east. This is a simplification in which I take all comers when they come. Okay? And so if I make those assumptions, this is what the average dispatch plan would look like. And notice a couple things. One, I wait, I accumulate, and once I start, I'm in operation continuously until the end of the horizon. And every dispatch, I expect on average to be decreasing in length. So the first dispatch is the longest, the second dispatch is the second longest, the third dispatch is the third longest, or the shortest in this case. So the average behavior of my system reflects some of the structural properties that I was identifying in my very simple models up front. So that's kind of a nice sanity check. So then this is the example of many vehicles. So let's now look at the one vehicle case. What is that going to look like? In a sense, it's going to be very, very similar, but a little more complicated. What's basically going to happen is I'm going to wait until some point in time, and from that point forward, the vehicle is going to be in continuous operation until the end of the horizon. So exactly as we had described before, I have an off period in which I accumulate orders, and then once I start operating, the vehicle is in constant operation until the end of the business day. And I have, again, decreasing dispatch lengths because at the beginning of the day I'm banking many more orders, but as I get closer and closer, I have much less of a wiggle room of how far the vehicle can go and what it can do, so it has to take fewer orders. Okay? And in both cases, this is going to basically this is predicting what might happen on an average operating day. And I can tell you I did not include the slide here, but we've done validation experiments, sort of saying, okay, this looks nice, but does this actually work? And so if you, for example, were to calibrate something like this, so you say, okay, what does my service region look like? And let me fit a routing approximation that captures the travel times in traffic and the topology of this network. And now based on this approximation, let me make predictions about what would the actual operating day look like if I simulate different days in which I simulate orders showing up in different places, at different times. And the predictions are remarkably accurate. So we had one example in which we do a setup just like this in which we predict 3 dispatches, and we predict, roughly speaking, on average, your first dispatch will take these many orders, the second dispatch will take these many orders, and the third dispatch will take the remainder. And we observe something like in 98% of the cases there's 3 dispatches, and the average that we take, the empirical average we observe is on the nose to what we're predicting. So this is actually going to tell you how the system is going to work most of the time. And so then let me give you an example of then how do you actually make decisions with these kinds of models. So imagine that I tell you that you have a distribution center that services an 8 by 8 mile service region. And we expect, we have over a 10-hour service window for same-day delivery. We expect about 75 orders to show up. And we have a vehicle, we're conservative and we're going to assume that the vehicle travels at about 25 miles an hour on average. And there's a 1-minute service time to deliver the order, so the time that it takes for the driver to park, drop off the order, and start up again. And we're going to assume Manhattan distances here just means rectilinear distances, so sort of the more reflective of an urban road network, right, where you're mostly moving east, west, or north, south. Okay? So under these conditions, what do we expect to happen? What if we wanted, well, the question here, the sort of the illustrative question here is, what if we wanted to use many vehicles or just one vehicle? What would be the difference? And so if you crunch the numbers based on the examples I just showed you, if you use many vehicles, it turns out you only need 2. And the first dispatch will take about 64 orders on average, and the second one will take the less 11. But if you only use one vehicle, you have a slightly more symmetric dispatch plan. The first dispatch takes about 55 orders on average, and the second one takes 20. But the remarkable thing is if you look at the expected routing cost of both of these solutions, there's an increase of only 4%. So what you're basically saying is you're dedicating an extra resource to this operation, and if you take that resource away and you cut my number of vehicles in half, my routing time or routing cost only goes up by 4%. So that seems like a no-brainer, right? Yes, Martin.
When is the first dispatch starting for the 2 vehicles and for the 1 vehicle? Because it may be that the 1 vehicle needs 4 hours in total. And
well, it's proportional to 64 and 55. Right? So I'm not doing the math here, but let's see. So 75 orders over 10 hours would be, so if you do if you divide 64 by 75, that's the time of the first dispatch. If you divide 55 by 75, you get the time of the first dispatch for each of the two solutions. So it's proportional. So it's certainly going to be the case that the vehicle is going to be operating longer, but the dispatch time increases by only 4%. So that tells you how much longer the vehicle is, the single vehicle is in operation compared to the two vehicles in the many vehicle case. Now, a different possibility here, something else a manager might do instead, is to say, well, suppose I've already dedicated two vehicles to this operation and I don't want to take one vehicle away, I have no other use for it at the moment, then an alternate thing to do here is to say, well, I might notice that the second dispatch has a bunch of slack. And so instead of taking only 11 orders, I might say, well, I'm going to increase the 75 to maybe, I think I did the numbers and it was 79, right? So I'll take 4 more orders, and that still gives me enough time to come back right at the deadline. So on average, right? So if on average, I can accept orders past the 10-hour service window that I establish, I can in fact take orders for maybe another 30 minutes, right? So maybe the way to say it is not that I'm going to take 4 more orders, but rather I'm going to keep the service open for another 30 minutes. And without changing my resources, I can still serve that. Yes?
From my perspective in the industry, I'm saying, oh, I can have 2 vehicles, more flexibility, less risk, for only 4% more.
4% less?
No, I can have 2 vehicles for only 4% more cost than if I had only 1.
Oh, no. This is the dispatch time increase. So this is saying how much the total routing time of the 2 dispatches here is 4% higher than the total routing time of the dispatches here. So what this is saying is if you wanted to dedicate, so if you didn't want to have the fixed cost of having 2 vehicles dedicated to this service, then the operating cost would go up by only 4%. So in some sense, you're saying if you have 2 resources, then your operating cost would be lower, and if you're okay with the dedication of the 2 resources to this service, then that's how much lower how much lower the operating cost would be. But in that case, I would also then say you can also at that point extend this service window another 30 minutes on average. That would be another possibility here. And so this is essentially the kind of analysis that we're doing with these models. Other questions? Terrific. Okay. So wrapping it up. I'm very excited by problems in e-retail, by problems in the last mile. I think there's a lot of cool stuff happening in this space. Specifically for same-day delivery, it makes everything really challenging, which is in a sense good for us, keeps us in business. Let's say if you wanted to sort of think of what are the fundamental trade-offs when you're making the dispatching decisions and when you're operating the system, it's really these 2 things right here, right? I have to decide, do I keep my vehicle at the depot? Do I wait and get more information? But then if I wait, I am less flexible later, or do I dispatch the vehicle now, but then the vehicle is not available when new things come in? And if I decide to make the dispatch, do I make a short dispatch, which brings the vehicle back sooner and lets me update more and be more nimble, or do I take advantage of economies of scale and dispatch it for longer? These are interesting, difficult questions, right? This is basically what makes the problem so interesting. And what I've basically hopefully argued here for a little bit is on the operational side, you can start with a very simplified problem and still derive some useful structural properties that will help your dispatching plans. But if you want any hope of actually having low-cost dispatching plans, you do have to be adaptive and nimble. You have to incorporate information as it comes in and be dynamic. And on the tactical side, the average behavior is surprisingly reflecting a lot of the properties that we saw in the operational models. And the other interesting thing we notice is that the economies of scale in these tactical models tell you that there's going to be, let's say, maximum asymmetry. So you will not use your resources equally. In fact, what you want to do if you're optimizing your routing costs is to use them as unequally as possible, which is kind of a weird thing to think about, right? If you're thinking of fairness, if you're thinking of how long two different drivers are working, if you're thinking of the depreciation or what's going to happen to the two different vehicles, if you're not careful, you're going to have an unequal utilization of resources. And in general, this also leads to lots of interesting questions. So thanks very much for your time. Yeah.
How is the problem changing now with drivers on demand?
Yes, this is something else that a lot of us are looking at. So in some sense, you can think of one of the versions of our problem, the version where we say we outsource whatever's left, as the version with drivers on demand. Although, of course, what's happening in a lot of situations is that's becoming the bulk of the operation. And I would say there's many, many interesting questions that come up in that case. One of them being, in some sense, you now have a marketplace, right? It depends on what kind of drivers on demand you have, but if you really are talking some kind of an Uber model, then it's a marketplace, and now you have to worry about pricing on both sides. You price the service to the customer, and you price the delivery cost to the driver. So that I'm telling you, I mean, I'm very excited by these kinds of problems. They're very interesting, and I think there's lots to do there too. Yeah. Other questions? Yes.
So does this research, does it feed into, I mean, do companies develop like in-house software or custom software to address these routing problems, or does it kind of speak to like how they fundamentally do business if, you know, last mile routing is?
Yeah, so both. I think our thought here, our thought process was on the operational questions, this would really be how would you design a software, a dispatching algorithm that would help in the actual day-to-day decision support of the operation of a warehouse. And we have talked to, let's say, companies that shall remain nameless about kind of what they do, and they take our, you know, but they give us some feedback on these different questions. And then on the tactical side, the question there really is, should I offer this service? Where should I offer this service? How big should my service area be? These kinds of questions, and that's more what we're hoping to answer with the second set of results. Yes. Yeah.
So for your problem on the line, if we want to implement a service area sizing, where we size a service area dependent on the time of the day, you showed that the dispatch lengths are monotonically decreasing.
Yes.
Can you use that? Can you somehow prove that the optimal policy for sizing is also monotonically decreasing?
So this is a problem I find very interesting, and we're thinking about it right now. Yes. So some of the structural results that I've showed you so far sort of indicate that you might even want to think of designing a dynamic service area, right? Earlier in the day, the service area goes farther out. Later in the day, the service area comes farther in, comes closer in. This is definitely an interesting question, for sure. Well, thank you very much.